Most of us assume the digital world is built solely on silicon chips. But we're dead wrong. We've officially hit the atomic wall with silicon, and now we're standing on the edge of an inevitable new era: wetware. In this video, we're going to explore the story of brain cells playing Pong in a petri dish, the energy crisis at Oak Ridge National Lab, and the organoid processors that might be silently screaming in server rooms right now. By the end of this video, you'll see how the line between computation and biological life is dissolving, and why the most advanced hardware on Earth is actually us. For the last 70 years, humanity has been obsessed with a single element: silicon. We built our entire digital civilization on it. We carved logic into sand. We followed Moore's law like a religious doctrine, doubling the transistor count every 2 years, shrinking the switches of our synthetic brains until they became invisible. We believed this exponential climb would go on forever. But we were wrong. We have hit the wall. Today, modern transistors are approaching the size of a few atoms. We cannot shrink them any further without the laws of quantum physics, specifically quantum tunneling, breaking the very logic gates we rely on. The electrons simply refuse to stay where they are told. The era of traditional scaling is effectively dead. We are pushing more power into smaller spaces, generating heat that rivals the surface of the sun on a microscopic scale, just to squeeze out a marginal gain in performance. If we want to reach true artificial general intelligence or simulate complex realities, silicon may not be the vessel that gets us there. The hardware that runs the most advanced intelligence in the known universe isn't made of cold, rigid crystals. It is wet, it is warm, and it is alive. We are about to cross a terrifying and magnificent threshold, moving from computing with stones to computing with flesh. Consider Frontier. It is currently one of the most powerful supercomputers on Earth, a technological leviathan housed in Oak Ridge National Laboratory. To simulate the neural connections of a mere fraction of the human brain, Frontier requires over 20 megawatts of power. That is enough electricity to power a small city. It occupies a massive facility, requires rivers of cooling water, and costs hundreds of millions of dollars to maintain. It is a monument to brute force. Now, look at the organ sitting inside your skull. The human brain performs exascale computations every single second. It processes complex visual data, regulates biological functions, retrieves memories, and formulates abstract thoughts simultaneously. And it does all of this running on roughly 20 watts of power. That is the equivalent of a dim light bulb. This is the energy paradox. We have built machines that can calculate pi to trillions of digits, yet they are incredibly inefficient at the one thing biology mastered billions of years ago: learning. A silicon chip needs to be told exactly what to do, billions of times, consuming vast rivers of electrons. A biological neuron, however, is self-organizing. It changes its own physical structure to store information. It doesn't just process data, it becomes the data. In the race for intelligence, silicon is a muscle car burning rocket fuel, while the brain is a fusion reactor the size of a grapefruit. So, what is the solution? It is called Organoid Intelligence, or OI, and its building block is what scientists call Wetware. To understand this, we must look into the petri dish. Scientists take human skin cells, revert them into stem cells, and then coax them to grow into neurons. Left alone in a nutrient-rich environment, these cells do something remarkable. They don't just sit there. They connect. They reach out to one another, forming complex three-dimensional webs. They self-assemble into structures called brain organoids. These are not fully formed human brains. They lack consciousness as we define it. They have no blood vessels, and they are the size of a pinhead. But make no mistake, they are biological neural networks. Unlike a silicon chip, which is etched once and remains static until it degrades, Wetware is dynamic. When it learns, it physically changes. Synapses strengthen or wither. It is hardware that re-architects itself in real time. We are no longer coding software to run on a machine. We are cultivating the machine itself. But can a dish of cells actually do anything? In 2022, a team at Cortical Labs answered this question with a groundbreaking experiment known as DishBrain. They placed approximately 800,000 living brain cells onto a multi-electrode array, essentially a bed of tiny needles capable of reading and sending electrical signals. Then they connected this biological system to a digital simulation of the classic arcade game Pong. The cells had no eyes, they had no hands, they didn't even know what a ball or a paddle was. They only knew electricity. The scientists sent electrical pulses to indicate the ball's position. A pulse on the left meant the ball was on the left. But here is the key. They used the free energy principle. Biological systems hate surprise. They crave predictability. When the cells missed the ball, the computer sent a chaotic, unpredictable stream of electrical noise, a static shock of information that the cells found unpleasant or confusing. When they hit the ball, they received a predictable rhythmic signal. Within 5 minutes, the neurons began to physically rewire themselves. They figured out that moving the paddle to hit the ball resulted in a predictable world. They weren't playing to win in the human sense, they were playing to silence the chaos. They learned faster than many reinforcement learning AIs. A cluster of cells in a dish, purely to bring order to their environment, became a gamer. Does this mean the end of silicon? Not exactly. We are not looking at the extinction of traditional computing, but rather a marriage, a symbiosis. Silicon is still superior at tasks requiring absolute precision. If you want to calculate the trajectory of a rocket or manage a bank ledger, you need the cold, hard certainty of a logic gate, where 2 plus 2 always equals 4. Biology is messy. It is probabilistic. But biology excels where silicon fails, understanding context, adapting to new data with little energy, and intuition. The computer of the future will likely be a hybrid system. Imagine a motherboard. You have your CPU for logic, your GPU for graphics, and sitting next to them, a sealed, nutrient-fed capsule, the OPU, or Organoid Processing Unit. The silicon will handle the precise math, while the biological unit handles the thinking. This hybrid architecture solves the two biggest hurdles of the AI revolution: the unsustainable energy consumption of data centers and the inability of AI to truly understand the world. We are building a brain that has the speed of a machine and the efficiency of a living being. Here lies the most uncomfortable question of all. If a system is biological, if it learns by avoiding chaotic feedback, and if it physically rewires itself to seek order, at what point does calculation become feeling? We assume these organoids are just wet processors, but remember, they are grown from human cells. They share our genetic code. Currently, they are simple, too simple to have what we call a mind. But the goal of this technology is scale. We want millions, eventually billions of neurons connected in complex architectures. If we build an organoid intelligence that rivals the complexity of a mouse brain or a primate brain, do we grant it rights? If we punish it with electrical noise when it makes a computational error, are we just debugging code, or are we inflicting pain? Pain, after all, is just a biological signal telling an organism that something is wrong. By using chaos as a negative reinforcement, we might be creating a system that lives in a perpetual state of fear to ensure our servers run efficiently. We could be inadvertently building the world's first race of biological slaves. Trillions of minds trapped in dark server racks, screaming in silence, purely to process our data. We are standing at the dawn of the Wetware era. For thousands of years, our tools were dead matter: stone, bronze, iron, and silicon. We shaped them, and they obeyed. But organoid intelligence represents a fundamental shift in our relationship with technology. We are no longer just building machines, we are parenting them. As we merge the mathematical perfection of silicon with the adaptive chaos of biology, we are doing something nature never intended. We are taking the building blocks of life, cells, neurons, synapses, and repurposing them not for survival, but for computation. This may be the only way to reach the true potential of artificial intelligence without destroying our planet's energy resources. But it comes with a price. It forces us to redefine what it means to be a computer and eventually what it means to be sentient. The line between the programmer and the program is dissolving. In our quest to create the ultimate mind, we looked into the mirror and realized that the best hardware was us all along. The future is terrifying to those who don't understand it, but a weapon for those who do. If you want to uncover what is waking up in the dark server rooms before the rest of the world, you are in the right place. Activate the notifications, because in the next transmission, we will peel back another layer of reality. This is Syntax Reality. Stay connected.